impossible ones. They weren't really impossible, but I did the trickier ones. So, you can kind of skimp on some of the notation here by saying, okay, I know what really I'm getting after here. Based on the examples that we covered, it really is just a matter of taking the antiderivative of each component with respect to t. And then once you do that, you just have to get a constant of integration tacked on specific to that component. Right? So for the first one here, we're looking at t cubed plus t squared plus c sub I. Right? So that would be the coefficient of I. Then we'd have, bring down the positive sign, antiderivative of t, 3t would be 3/2 t squared minus 6t plus cj, constant of integration specific to the j component, and then multiplied by the unit vector in the direction of j. And then finally, last but certainly not least, smidge this over. Anti-differentiate this piece. We'll do it in black. 3/2 t to the 4th plus 5/3 t cubed minus 4t. I'll move this down here before I can write the rest. We'll just box that in so it makes it a little bit more obvious what that's referring to. That's not what I wanted to do. Do it this way. All right, so plus 4t, or minus 4t, plus the constant of integration in the direction, or specific to k, multiplied by the unit vector in the direction of k. All right, so the size of the writing here is a little elementary schoolish, but these should be problems that you look forward to on an assessment rather than dread. All right. I had a little stray mark that I had to erase just now. I don't know where it came from, so I'm worried that it was important. Hopefully it's not, but we'll see. Looks like everything's right. I don't think I lost it. Maybe it was just like crossing the T somewhere. I'm just double checking everything because I want to make sure that I didn't screw something up. Good. I think so. Oh, if I missed something, you'll tell me. All right. Now the last bit there, that one is a definite integral. So you kind of look at it and say, well, what do I do? Well, you do the same thing you do when you have an indefinite integral, except you have the bounds, right? This one's a little bit on the spicier side. Well, I'll take you through the problem and I'll show you. You could create the parametric curve to get a sense of what's going on before you even get started. Sometimes that's a worthwhile use of your time, because if there's going to be a discontinuity along the way, that would bear itself out. It's just one thing you got to be careful about. And so this interval for the integral that we're dealing with here, it's not troublesome. 0 to pi over 3, there won't be any instances in which the function is not differentiable, not continuous. But you can kind of imagine a situation where it could easily happen. You go from 0 to 2 pi over 3, all of a sudden you got pi over 2 in that interval. Pi over 2 leads tangent to be undefined. All right, so sometimes just taking a quick look at the picture goes a long way. And you know what? you don't even have to take a look at the picture as a parametric. Take a look at the picture for each component separately from one another. All right. So, I mean, if you want, you can do it with a restricted domain. But if you have a sense of where pi over 3 is, you're really just kind of looking in that window. So you could just say y equals sine 2t, so 2x I'll use. Then we'd have tangent, so y equals tangent of x, and then e to the negative 2t. So negative 2x. And just make sure there isn't any, like I said, funny business going on. And you'll see that for the tangent function, there's many instances in which there's some funny business going on. But if you're focusing only on the interval of 0 to pi over 3, and don't worry about the steps or anything like that. You just look at that interval, you could see each component. I mean, you're not proving anything here. You're just looking to see that each component is good to go in its own right. Right? So that's a way of handling it. You may also consider writing it as f of x for each piece, f of x, g of x. And, whatever you want of x, so h of x would be next on the list. For the sake of Desmos, meaning to make it so that Desmos can easily understand what you're asking it to do, if you needed to do some substitutions or things like that. But in terms of the setup, this is the same as saying, let me make that a little thinner, on the interval of 0 to pi over 3, with respect to t, we have sine of 2t. Let me go sine of 2t, and this is the I vector. Okay. Then we would do the same thing, but for tangent and for the E component. So a little bit of copy pasting. So we'd have tangent, and that's the J, and e to the negative 2t for k. We're in prepare for the worst and hope for the best mode, hopefully. Hopefully you all agree that that's a good mentality to have in this class, which means that, maybe this is a show all your work situation. That's preparing for the worst. Hoping for the best, maybe it's just a simple multiple choice question. Right? In which case it's a pop it into your calculator, call it a day. Right? So we prepare for one and settle for the other. Right? So antiderivative of sine of 2t, we've been down this road before. That's going to be, let me get my my writing instrument up here. So negative, and again, I kind of have this mentality, and maybe I spend a little too much time going over basic antiderivative rules, but in my experience, people have struggled with that in the past. So I just assume that maybe you kind of use the refresher on it. When I look at a simple trig function, even if there's a coefficient, I look at it like, all right, I know that it's negative cosine. But if I were to take the derivative of this, I would get sine of 2t times 2. I'd get exactly double what I want, so I correct for that by slapping a 1/2 on in front. Now, some of us are rules people. The rules folks, they look at it and say, well, I just knew it as antiderivative is negative cosine, and I just divide by whatever the coefficient of t is. That's fine too. All right, whatever lets you sleep at night. Nah, it's whatever you understand. All right. So that is going to be my I component. All right. Tangent of t, you could kind of look at that as a rule, or you could look at it as a U substitution problem. All right. So it's really just a matter of where your comfort level is. So if you know the rule, then go for it. If you don't know the rule, then well, then don't go for it. That's all I can really tell you. But I'll just take you through it very quickly, like as quickly as I possibly can, without boring people to tears. So we know that this is the same as sine of t over cosine of t. If I'm integrating this, what I'd be looking at, whenever I see a fraction, I think natural log. So I'd be looking at the natural log of the cosine of t. Now, if you play that out logically, if I say d dt of the natural log of the cosine of t, it would be 1 over the cosine of t times the derivative of cosine of t, which is negative sine of t. All right, so I would correct that by saying, okay, well, it's definitely not natural log of cosine of t, but it's close. I don't want the negative, so I can negate this. All right, but going back to basic, like one of the earlier rules that you learned when it came to logs and exponential functions is the power rule for logarithms, right? And that is that the exponent jumps over the log like a frog. Of course, that's the technical definition. No, it's that's the mnemonic device to help you remember. But it just means that coefficients become powers, powers become coefficients. Right? So this would be the same as the natural log of cosine to the negative first power. Cosine to the negative first power is the same as secant. Right? So the antiderivative of tangent is going to be the natural log, so plus natural log secant t on the interval of 0 to pi over 3. All right, so that's our second component. I also need my j. Poor quality j. Fix that. Just kind of piecing it together. All right. Last up is the exponential. Exponentials are pretty easy as long as they don't have anything too crazy in the exponent themselves. And that is plus. So we know it's going to be e to the 2t in some capacity. If I were to take the derivative of this, it'd be e to the negative 2t times negative 2. I need to correct for that. So negative 1/2. And you can merge that with the plus sign if you want, but I'm not going to, at least not yet. On the interval of 0 to pi over 3. And that's going to be my k component. So then I just need to evaluate these, and that in and of itself shouldn't be too bad. Oh, I lost my t. All right, so I just got to evaluate this, which involves knowing some trig rules or being handy with a calculator again. But it's not, this should not be the hard part. All right. So negative 1/2 cosine of 2 pi over 3 is 1/2. minus, and I'll actually do that as a binomial. Cosine of 0 is equal to 1. We'll clean it all up in a sec. All right, so I'm just popping it all in. Oh, sorry, it's negative 1/2. Yeah, so, and then, there we are. Now the next piece, I don't expect to be quite as neighborly. It might be all right in terms of getting a result. I just don't think it's going to be anything that we're going to be able to simplify too much. But the natural log of secant of pi over 3. Secant pi over 3 is the reciprocal of cosine pi over 3. Cosine pi over 3 is 1/2. Reciprocal of that is equal to 2. So we're looking at plus ln of 2 minus, now secant, again, reciprocal of cosine. Cosine of 0 is 1. Reciprocal of 1 is 1. Natural log of 1 is equal to 0. I'm going to write the minus 0 here as a placeholder so that you know that the computation was carried out, but we wouldn't really need to write it. So it kind of cleans up, but not in a beautiful, like, oh, this is so nice kind of way. Also, I don't need the absolute values anymore because there's no way for 2 to be anything but a positive number. So I can just pop that in there and leave it as is. All right. Now, the last bit, there's really nothing I can do except to pop in the pi over 3. So minus, I'll leave the plus actually. So plus, we're looking at negative 1/2. We'll leave that coefficient separate. E to the negative 2 pi over 3 minus, so I'm really just evaluating this piece. I'm holding that negative 1/2 constant. So minus a 1. All right. And then we can see what this does in terms of simplifying. I thought you said you did all the easy ones. I really did, because like I said, if this was a multiple choice question, you would have been done with this before I even wrote down the question here. So that's kind of what I mean by that. But we're looking at 1/4. Well, actually, let me just do the parentheses first rather than multiplying. So negative 3/2 times 1/2 is going to be 3/4 plus ln of 2 minus 1/2 e to the negative 2 pi over 3 plus 1/2. So we can merge these two bad boys. All right. So that's going to be 5/4. So what I'll do is I'll just wipe this out and make this a 5/4. The strategic use of an eraser. Oh, wait, no, I can't do that. I'm sorry. I'm out. Sorry. I got a little too overzealous here. Back it up. Just back it up. Just back it up. Forgot my I, J, and K. Actually, honestly, full disclosure, completely forgot what course I was teaching.
I was going to tell you that if you were going to put the I, J, and K.
Yeah, that is that's kind of a big deal, right?
Yes. So the secant of pi over 3 is 2, right? Is that 2?
The second.
Secant.
Oh, secant is 2. Yeah, secant pi over 3 is equal to 2. Exactly. All right. So let me. Well, I don't want to just tuck it in there without At least moving some things around for, oh, get over there, son of a gun. Well, fortunately, it was only that one little thing, it looks like, anyway, that I snafu'd. Now, for this one, honestly, I think I was, as it turns out, because distributing didn't really serve a purpose, I'm probably better off, just for the sake of signage, just leaving it the way it was. I'm going to bring just this whole business down here. Yeah, so it really turned out that it was the first thing and the second thing that I can clean up a little bit, but then after that, that was really it. I don't want to mess with that. Okay, so yeah, that's something. Anyway, so let me go through the Desmos approach. So it's like, let's start this whole problem over and take it from a different perspective, right? So in your functions menu, under miscellaneous, you have your antiderivative component. We're going from 0 to pi over 3. If it'll let me. Yeah, there it is. I'm just leaving it in terms of x. That'll spit out the 0.75 or the 3/4. I mean, I have faith that we all recognize that 0.75 is 3/4, but just in case you get some funky decimal that maybe you don't recognize, you tap on the fraction converter icon and it'll convert it over for you. We can't expect really the same thing to happen when it comes to natural logs and radicals and things like that. So we kind of take it where we get it. The duplicate function is your best friend when it comes to this, because here I can just change from f to a g, and that'll refer to my tangent function still on the same interval. So now I have the second component. Now we just gotta, I mean, there's a couple ways to handle it. And it's never going to be a satisfying answer for what I say here, because you do have to have a sense of what the antiderivative is in order for this part of the process to actually work out. But if you know that your answer is supposed to be the natural log of something, then what you can do is raise this expression, make it the power of e, and that'll give you the number that's contained within the natural log, right? So I just for the sake of brevity, what I'll do is I'll just type it in. I'll just type in a bunch of digits. And you can see the more digits that I type in, the closer it gets to being a 2. So that's 0, 5, 6. And, you know, like if you're as accurate as Desmos was in reporting the answer, then it should spit out that value to you, right? Because really all a natural log is asking you is, what does that base have to be raised to? So in the case of a natural log, the base is e. What does the base e have to be raised to in order to give a result of 2, right? So we just needed to know what the value was that was contained in the natural log. So it's e raised to that decimal power, right? But if you had no idea that the antiderivative of tangent even involved a natural log, then that doesn't really help you. However, since every test is an open notes test, there's really no reason why you shouldn't be able to access that information, whether it's by looking it up real quick online, or if you have it in your notes or something like that. You know, the only danger behind an open notes assessment is when you have too many resources and you spend half the time kind of fumbling through all the things looking for you know, the perfect resource to meet your needs. the people who have been running or tipping, I don't want to claim it for this class, but this year has been kind of a novel experience. And what I can say is that across all of my classes, so I teach AP Stat, I teach statistics here, I teach math for elementary school teachers, I teach this course, I teach Calc 1 in the high school, the equivalent, the high school equivalent of Calc 1. I teach Algebra 1, and I've been tutoring people and helping people along the way. The one commonality that I've noticed is that people are looking online or in their notes when they come across a problem on a test. They're looking for the one that matches the question on the test, so that they could just kind of like, all right, he used a 2 here in my notes, but he's using a 3 on the test. So I'll just rewrite everything that I had in my notes, just swapping out a 2 for a 3. It's never really going to be like that. But if you have little notes to yourself, like when I see this, do that. When I see that, do that. Little like tips to yourself, so that when you come across those kind of problems on the test, it does go a long way. You know, just a thought, because good luck if, you know, in the next step here, when I take this guy, pop an H in there, yeah, you look at that and you know, if it gave you a decimal, I'd say good luck in getting it into the appropriate form, where you'd say, oh yeah, clearly that decimal is -1/2 times e to the -2 pi over 3 minus 1, right? That the calculator, or the Desmos calculator, just kind of gave up on that one. Let me just get rid of that. Right. Well, actually, it didn't give up. It just got confused because I had 2 h of, even though it's the same h of x, it got confused. But still, you look at it and say, well, how am I going to know that that's equivalent to -1/2 e to the blah, blah, blah? Well, the short answer is you're probably not. So you got to do something on your own. This is a good way to check it. So the first part you could do completely on Desmos. The second part, you're going to do it on Desmos until you realize, oh, okay, I might have to do a little bit by hand, and then use Desmos to support your work. The third one, the third component, you're probably looking at and saying, all right, I got to do this part by hand, but at least I can check it on Desmos, right? So, because that's just pretty much how it's going to be. There are exceptions to everything. You know, every time there's a rule that's created, there's always someone out there trying to figure out a way around it. You know, you can try to go to online resources that'll have you do the work for you. I'm not very forgiving when it comes to that, because what ends up invariably happening is that I start seeing some notation that students put down as answers on my tests, and I'm like, oh, where'd you learn that notation? Because we didn't cover that in class. I'm like, I know where you learned that from. You learned it from Wolfram Alpha, where you had them do the problem for you. Oh, you sprung for the premium package where they show you the work too. However, that's not the way we did it, so I'm not giving you any credit for that. So, you know, developing good notes and resources to help you navigate through an assessment, that's kind of where you want to spend your time and energy. You saw it today, hopefully, and if you didn't, it's available. I don't hide what kind of questions are going to be on a test. So take a look on Blackboard. Again, if you haven't already looked, I give you the whole breakdown. You know what's going to be on it. It's just a matter of, you know, just getting your notes looking good. You know, get to know Desmos. If you haven't taken the time to get to know Desmos, for crying out loud, I don't know what you're waiting for. Right? Take your time between Desmos and GeoGebra. They're valuable resources. In a lot of cases, they're going to do the work for you. And I got to tell you, and I mean this from the bottom of my heart, there are problems that I put on a test where I know damn well that it'll take you 10 seconds to do if you know how to use Desmos. It'll take you an hour and a half to do if you don't. Right? So definitely take your time. If you haven't created a Desmos account so that you can save your work, again, don't know what you're waiting for, because I got my little drop down here. Look at all this stuff I got. Every time I create something, I'm like, you know what? Why not save it? You know, you don't even have to know what half of these things are. Like, what's an exit ticket? Who cares? all you need to know is that, hey, I got one that talks about 5-number summaries. I have one that talks about box plots. You know, in this class, piecewise functions, right? Slopes, things like that. Every time I create something that's substantial, I save it. You could do that too if you haven't already been doing that. Right? That's the pep talk for the night. Right?